Hello, this is Dean Banerjee, and today we're going to talk about using the National Clock Design tool to simulate the performance of a design. At this point, we're going to assume that there is a design already made and created and the part is already chosen. If this is not the case, or if there's a question about how to do that, we have some other videos related in this series that discuss that in depth. So now we're going to assume that we've chosen a part. So the different things we can simulate, pretty much we have a phase noise, we can simulate that, or we can simulate the Bode plot. So let's talk about the Bode plot first. The Bode plot simulation basically shows you the Bode plot. It shows you the closed loop transfer function. It shows you the phase as a function of the frequency. You see the VCO transfer function. We can simulate those curves. You'll notice in this screen we also have this option, copy traces to clipboard. So if we wanted to copy these traces, just click this. That copies it to the clipboard. Then you can go into an application such as Excel and hit Control-V, and then you have all the data for that. So that's what this feature does. So in the simulation, we can do that. You see that we have the loop bandwidth, we have the phase margin, we have some other parameters of the filter here. These are actually discussed in the Clock Designer's Manual and the PLL Design Handbook, but it takes a little bit of time to discuss those, so I'm just refer you to those references if you're interested. So this will show you the Bode parameters. You know, one of the things that's also very useful, let's suppose there's a design that perhaps there's an inherited design that you did not design, and you want to know what are the properties of this. For instance, you could type in any values here. It doesn't have to be what was designed for. And you can do this, and then if you look here, we can go ahead and see the plot has already updated. You see the phase margin has changed and loop bandwidth has changed. You can see, let's go look at loop bandwidth here, phase margin here, keep an eye on that. I'm going to change the charge pump gain. See the effect of changing the components, changing the charge pump current, changing the phase detector frequency. If you change, in this case, the phase detector frequency changed with the end in. So if I was to change this to 1200, you can see the effect of changing all these things around. So let me go and reconfigure this back to the way I had it. And okay, so now I have things back the way we had it. So that pretty much covers the Bode plot simulation. Now the other thing we have for the simulation on this is actually the phase noise. So if we look at a block, you can look at any block and simulate what the phase noise would appear at the output of this block. So in this case, here's the oscillator. For this design, we never really specified what the oscillator phase noise was, and the assumption that the program makes is the oscillator phase noise is actually quite good. But you can always change that if you want. For instance, of these options here, we have enter custom phase noise, copy traces to clipboard, which does a similar thing as Bode plot and close. If you wanted to enter a custom phase noise, let's go to that one. If we say enter custom phase noise, I can go here and enter in. I can enter in offsets and phase noise, like so. Go ahead and set the noise. And once I do that, I've set the noise, and you see it will accept this phase noise that I've entered, and it will try to extrapolate what the phase noise would be for between the points. I could go over here, and if I go and just type in the values I want for the offset, you see it will adjust the phase noise and try to calculate what that would be. You see here it calculates the jitter. You can see in this case it's analyzing the total trace, which is the same as os-in. So we'll look at this in the VCO when we talk about that. But let's talk about the frequencies. You know, where is the jitter being calculated from? In this case, 1K to 10 megahertz. If I want a different frequency, change these frequencies around, it's actually calculating jitter over a different range. So that's how that integration thing. Now, one reason I showed the oscillator block first, I wanted to show this feature, enter custom phase noise, and we did this by entering values, and this is great for a datasheet application. But there's also features, load noise from file. In this case, I'm going to actually load in the phase noise, and this is a scan 25100. This is a SerDes part, and this is a recovered clock. So I've actually saved this, and let's suppose this is a clock cleaning application. So I load this in, and this is what a recovered clock looks like. This was measured on a phase noise analyzer and saved. So now I have this. Now I can analyze all the properties of this here. But let's go and try some other things. Now that I have this new noise source, We actually talked about loop filter design in another video, but if we are to go recommend and design and calculate, you'll see that with the noisy reference, the loop bandwidth is going to change if you use a recommend, design, and calculate, because it's trying to design for optimal jitter. So that's one case where the simulation and the design are closely coupled. In fact, there's a lot of cases where you might design something and tweak it back and forth. That's very common. So that's one of the things you could do that. Let's go ahead and look at the VCO. At the VCO, we can see here's the outputs. Now here we have a lot more contributors. We have the total, which is the black one, and you see the OSIN. In this case, it's a noisy reference. You see the noise it's attributing. You see all the other things. These are all the things that I guess would be upstream of this block, and this is the phase noise that they contribute as it trickles down. Now the other thing you see here on the trace, I'm looking at the total, but now I can look at anything downstream. Like if I look at OSIN, I can say this, if I was going to look at this trace, what is the jitter that is being contributed at the VCO output due to OSIN? I can see this. I can change this around and see all these different blocks here. I'm probably interested in the total jitter, but I might ask the question, well, what if I had an ideal OSIN? Here you have something visible and contributor. Contributor means it adds the phase noise, and visible means you see it. So if I unclick contributor, we'll see the RMS jitter should improve. It does. It still shows me the trace, so maybe I should hide it so it doesn't confuse. And if I wanted to say, what would this be for an ideal OSIN? There you go. We have other things. We have the unshaped trace. So this is the VCO trace. You see here's the VCO phase noise, so it's shaped by the loop bandwidth. Inside the loop bandwidth it's suppressed. So we can see this. In fact, if we wanted to know what's the jitter for that, we can do that. We can actually go over here if we are interested. What is the VCO phase noise at, say, 1010 kilohertz? We can figure that one out too. So that's that shows pretty much some of the phase noise analysis tools. Now there's other things we can do. For instance, on the loop filter, we have some diagnostic tools. I'm going to go ahead and enable the oscillator back and make it a contributor. On the loop filters, this is for diagnostic purposes. You could say, what is a 0 hertz loop bandwidth? In this case, it's just the VCO. But let's go ahead and look at another output. Let me go ahead and say this is, say, I'm going to pick an output here, turn it on. If I was to turn on another output, and I say, what is this phase noise? Now I see that, oh, the output divider actually also contributes even with this theoretical 0 hertz loop bandwidth. I could say, what is it for a infinite hertz loop bandwidth? So this is like all the PLL, the TCXO noise, all that goes through. So that would be this noise source. And we see that also the output divider noise also contributes. So we can do this theoretical case. This is good for diagnostic purposes. I could say, what would it be for a brick wall filter? And I enter in the frequency of my brick wall filter, and I can go and I see those things. And again, there's no need to go and close this box. I could just as well change this thing dynamically and watch it over in this window change, like so. So that's showing you most of those capabilities. The one capability and one case we didn't really talk about is on spurs and fractional phase noise. That's actually the subject of another video where I discussed that with the LMX2541. But you see we have all the global spur options. Right now it's disabled, and that's going to be the topic of another video. Thank you very much for considering National Semiconductor.